Hello guys. Today would be a short stream. Let's just go a little bit about computer architecture. We got to learn computer architecture. Let's do it together. First of all, let me check if the stream is fine. About computer architecture. We got to learn computer architecture. Let's do it together. So you guys can hear me and everything
First of all,
is
let me
fine,
check
right?
if
The stream is fine. Okay, so everything looks good. Let's go. Wait, let me adjust the bitrate. Okay, stream should be better now. 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 Okay, you guys can see my screen, right? If anyone is joining this stream, feel free to chat, feel free to post any suggestions, anything you want to share. Okay, so we were starting with pipelining. Let me just give you guys a brief introduction what we're gonna do today. So today's agenda would be like pipelining, which is like one of the most important topic of computer architecture, the backbone you can say. CPU pipelining. We'll start with basic implementation, then I think then after that we will try to learn hazards, then we will study topics like DMA and many more, many important topics we're gonna cover. Not today, but we will just touch the basic today, and I will continue this series of computer architecture. First, let's start with the beginning. Let me see if you guys first, then I think then after that we will. Okay, stream is fine. Okay, so first of all, let's start with analogy. Like let's just try to relate computer pipelining with real life. Let's say like we are delivering a bucket. Okay, we are delivering a bucket, and let's say one people is one man is one person is like trying to deliver this bucket. Like let's try to get a better example. Let's say this is the bucket, and we want to deliver it like from point A to, let's say, point B. Okay, so if a single person is trying to deliver it, he will just go from here to here to here to here to here, and then it will like move to point B. But let's say if we have a chain of person, like here one person, here second, here third, here fourth, and here fifth, then we just don't have to move it like from here to here. We can just pass it like to the person A to person B to person C to person D to person E. So in that case, we just like, let's say we have like 10 buckets, so we just don't need to give one person one bucket. We can just move it like one there, one goes, then the person A takes this bucket and pass on to him, I think you guys are understanding that. Let's take bucket 3. This person take it, pass it to him, he passes it to him, and he passes it to him. When this guy is doing its work, this bucket might have already been here. This bucket after that might already. So it's just a chain of work, and the distribution of work becomes pretty easy. Okay. By the way, I can like show you the notes that I'm gonna follow for pipelining. Okay, there's a note, and this note is from Go classes. You guys can search it up. Go classes computer architecture. On YouTube, there are I think pipeline is completely freely available for theory, and we will try to cover some codes also here, like how CPU pipelining codes programming actually works, like how fetch, instruction, decode, how their like internal architecture looks like for every sub part of pipelining. We'll try to do that, but first of all, let's just I think you guys just got the analogy of pipeline, why it like why how it can make our life easy. So let me show you guys. So basically, pipelining is an implementation technique which multiple instructions are overlapped in execution, and today pipelining is nearly universal. Yeah, that's true. Every CPU architecture uses pipeline. Okay, so let me show you how this instruction architecture hardware actually looks like. Yeah, you can also like we will also use ChatGPT whenever we will not understand some things. So it really makes understanding useful. Like I will show you guys. I will get stuck, I'll ask ChatGPT, and how I use it, I'll show you guys. Okay. Okay. So yeah, this is instruction execution. This is add R1, R2, R3, and this is load R1 to R2. And how this actually is working, you can like let's try to imagine it. This is program counter, this is instruction memory, and it works like this: fetch, instruction fetch, decode, and here this ALU is working, and then data memory. The chronology is something like this. Right, let me show you guys. Yeah, the chronology is something like this: fetch, decode, execute, memory, write back. Right. So the chronology is something like this: fetch, decode, execute, memory, write back. Okay, so Yeah. And this is like just the internal working. And uh, if you see this assembly part, let's see, like, let me show you guys. But well, like, explain me this picture that I'm going to send you.
Sure, send it over. All right, I'll take a look. This is the 5-stage MIPS instruction pipeline. First, we have instruction fetch. The PC sends the address to instruction memory and fetches the instruction, then decode, where it figures out what the instruction is and reads the required registers. Then execute. That's the ALU stage, where an arithmetic or address calculation is done. Then memory access. This is only used if the instruction needs memory. And finally, write back. The result is written into the destination register, like R1. Hope this helps.
Yep. So, like, that's this picture is defining like nothing very complicated. It's just the chronology of steps that goes on into pipelining. Okay, let's move on to the. It's just the beginning. Okay, we will understand like how things work under the hood. Okay, so it's a five-stage pipeline. It basically, like, generally we work on with five-stage pipeline. Okay. Okay, so whole struct divided into five stages. If a single unit, then one instruction take uh, 20 nanosecond. If we assume it like this, let's assume one instruction take 20 nanosecond. Then if pipelined, if we use pipeline, then how things will work? It would work something like that. First 20 into 1, cause where just one instruction is taking 20 nanosecond to presume, plus 99 into 4. Why 99 into 4? Because we are presuming that we have 100 instructions. So first instruction, first one, just take 29 nanoseconds, and after that it will take 4 nanoseconds. Why? Because 20 nanosecond is the first instruction and this is 5-stage pipeline. So all the other stages don't need to take like entire 20 nanosecond, because remember we took the bucket analogy. The first one needs to go like this to this, then this, but after that all the person 1, person 2 are there to help. They will just take the second one and pass it. From there the next one would come and pass it. So all the others one just need to take 4 nanoseconds, which is 20 divided by 5 cycles. Like we took the analogy of persons, here it will be 5 cycles. So 20 divided by 4, 20 divided by 5, which is 4. So something like this pipelining actually works. Okay. all the other ones just need to take 4 nanoseconds, which is 20 divided by 5 cycles. Like we took the analogy of persons, here it will be 5 cycles. So 20 divided by 20 divided by 5, which is 4. So something like this pipelining actually works. Okay. Okay, so let's take a 5-stage pipeline. C1, C2, C3, C4, C5. Let's just take 5 stages first. And this is how pipelining we like visualize pipelining. I'm trying to visualize a 5-stage pipeline. Let's say we have 3 instructions. First, let me draw the stages. So stages are fetch, decode, execute, then this memory, and write back. These are the pipeline stages. So let's say first I1 is working. So we'll have I1 here, I1 here, I1 here, I1 here, and then I2 comes. Let's try to different color. I2, 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 and then for I3, let's I3 will work like that. So it actually works something like that. Okay, so you guys can see that it generally likes getting less and less classes as it goes, as the number of instruction is growing, right? And as you can see here, it told us that it's a 5-stage pipeline, and wait, I actually sent it previously. Yeah, so this was a 7 cycle pipeline that I have created and asked ChatGPT about this. And here we can see that not very much change is happening throughout like the instruction, but when the classes are number of classes is low, we can see that first instruction took I1 5 classes, but after that it took only 4 classes, then 3. So they're taking less and less cycle time. in with pipelining. Whenever we see when we approach to non-pipelining, it will generally take much more clock cycle. Compared to so non-pipelining, it will generally take much more clock cycle. Okay, so next let's see. Let's take a quiz. Okay, so let's take this instruction pipelining quiz. If you have 5-stage pipeline and 1 clock cycle per stage and 10 instruction in our program, then when we use no pipelining, in that case there would be as 5 stage 10 instructions, so 5 into 10, 50 cycles. And with pipelining, there would be 5 stages for the first one, because the first one will go all the way as always, and remaining 9 instruction, let me show you guys like this. The remaining 9 instructions will only take one clock cycle per stage. You guys understood, right? As this is 5 clock cycles, as this is 5-stage pipeline, so it will have to go 5 for the first one, but after that only 1. So total will be 14 cycles. If there is explicitly mentioned that one stage is not 1 clock cycle, or like any other number other than 1 is given for per stage, the clock cycle, in that case will not take 1, will take that value only, which would be given. Okay, let's move on. So there can be also interstage buffer also, like yeah, when there would be these buffers, there might have these buffers. Whenever this buffer would be there, we will like add them in case of pipelining. In case of non-pipeline, we'll ignore them. You don't need to think about buffer. Okay, So that's some nitty-gritty things that we need to understand. Next, let's generalize the pipelining formula. Okay, it is a generalization of pipelining formula, which is instruction executions time. Okay, so for non-pipelining, we saw that y into tn. So tn is clock cycle and k is since cycles for first instruction y, cause k is number of stages. So k plus y minus 1. You guys can relate now. Okay, why, how is that formula came? Like, just see that question. You guys can relate. Let me just you guys can just see side by side. Okay. Let's see that cycle. Okay. Yeah. Y cycle time is 4 nanosecond plus 1 nanosecond here. Can you guys see? Because I told you whenever there will be overhead, we'll add it in case of pipelining. In case of if that was non-pipeline, in that case we will just take the sum of these. We just ignore the overhead in that case. But as it is a pipelining case, so yeah, we will have to take the overhead. And how that works, we will take the the slowest one with the slowest clock cycle. You can see that this is 4 nanoseconds, which is slowest here. Then the other 2, 3, 4 is the slowest. So 4 plus 1, 5 nanosecond one clock cycle. So let's do some questions to get this thing clear. You guys ready? Ready? It said that one stage is not one clock cycle, or like any number clock, any or like any number clock, any other number other than 1 is given for per stage, the clock cycle. In that case, will not take 1, will take that value only, which would be given. Okay, let's move on. So there can be also interstage buffer also, like yeah, cycle for non-pipeline to think about buffer. Pipelining, it is a generalization of pipelining formula, which is instruction executions time. So let's do a few questions. Stream is fine, I was just checking out the stream. Okay. Some few questions and we will move straight to hazards, because that's the part that I haven't studied yet. We will just learn it together. I don't know, maybe not today, maybe we'll do it tomorrow, because today is very late. Probably you can do this question. It's an easy one. So we have a 4-stage pipeline with stage delays 150, 120, 160 and 140 nanoseconds. Registers that are used between the stage have a delay of 5 nanoseconds each. Assuming constant clocking rate, the total time taken to process 1000 data items on this pipeline will be. Okay. So we have 4-stage pipeline and we have stage delays of like, let's just draw it. And stage delays of like 150, 120, 160 and 140. Okay, registers that are used between have delays of, they have like overheads of 5, 5, 5. All of them have 5 nanosecond delay. So what we can do, assuming constant clocking rates, the total time taken to process 1000 data items. So we have 1000 data items, like similar 1000 instructions. So the first instruction will take this is 4-stage pipeline, right? So 4 cycles plus other would take 999, 50. How much can you guys guess? Yep, 160 plus 5, because the slowest one will like make the difference. So 165, and if we take it, it would become let's see. Wait, sorry. This would be 1. Sorry, this would be 1. Pause. This is not clock cycle. This is like for 999. Let's just wait. Let's just ask ChatGPT to make sure. Yeah, just tell me. Okay, just tell me the question that I'm going to send to you. For that, the first instruction will take the number of stages, which is 4. So that would be 1 into 4. And after that, why 999 into 1 would be there. Let me send you the question.
Yeah, send it over. Doc? One moment. All right, here's what's going on. In ideal pipeline, the first item has to go through all 4 stages, so it takes 4 cycles to finish. After that, the pipeline's full, so every new cycle completes 1 more item. That's why you count 4 cycles first, then add 999 more for the remaining items. Total cycles is 4 plus 999, which is 1003, and the clock period is 160 plus 5, 165 nanoseconds. So total time is 1003 times 165 nanoseconds, which is about 165.5 microseconds. That's option C. And the formula to remember is number of stages plus number of items minus 1.
Yeah. Wait, like you said, total cycle is fine. You said that every new cycle completes 1 more item. But why not the first one? First one takes 4 cycles, and why the other 99 instructions take 1 more, 1 new cycle? No,
Right,
sorry.
so
Yeah, explain.
Yeah, that's okay. So the reason is after the first item spends 4 cycles filling the pipeline, every stage is busy at the same time. So in each new cycle, the last stage finishes 1 item, while earlier stages are working on the next ones. So nothing waits. That's why each additional item only needs 1 more cycle at the end to come out. It's not that they only take 1 stage, it's just that their work is overlapped. So think of it like an assembly line. Once it's full, 1 finished product comes off every tick.
Got it. So yeah, so that would be 1003 cycles, and total would be 1003 into 165 nanosecond, 165.5 nanoseconds. That was good. Let's just cover one more topic and we will continue with data hazards tomorrow. let's just see how the speed up works. So speed up is basically non-pipeline execution time upon pipeline execution time. That is what speed up is. You might have guessed it is just like intuitionally very common thing to expect. Okay, let's just take the problem. Just cover one more topic and we will they have like overheads of 5 5 5. Okay, let's take this problem. Okay, so it's two different machines. First has a single cycle data path with a cycle time of 15 nanoseconds. Second is pipeline machine with 5 pipeline stages and a cycle time of 3 nanoseconds. Okay. This one is first one is non-pipeline. So for non-pipeline, we'll just, I guess, clock cycle is 15. So bring this to clock cycle is 15 nanoseconds, and this is for first one, and for second one it is mentioned that it is a pipeline one, and we have 5-stage pipeline, and cycle time is 3 nanoseconds. So for this one, the number of instruction is n. The total time would be n into 15. For this time would be, as we know, first one will take 1 into 5 plus other, and here also we are taking instruction n. So n minus 1 into 1, because these are the cycles. Yeah. So 5 plus n minus 1, and total will be multiplied by clock cycle, which is cycle time, which is 3. So n plus 1 into 3. So speed up will be, what did we write? Non-pipeline execution time upon pipeline execution time. Non-pipeline was n into 15, and this will be n plus 4 multiplied by 3. Now the catch is, generally we know that the instructions are like in the range of 1000, 10,000, and very large, like in a CPU when a program is running, it takes like millions of instructions. So n would be very high. So you can just take limit. N tends to infinite. You're going to 15 upon 1 plus 4 of 3. So if we just use the limit here, let's just take this n here. So 1 plus 4 upon 1. Right, so this would become 0. So 5 would be the answer. Right, you guys got it, right? I got it. If I get it, you guys will definitely get it. So let's try one more question, shall we? Yeah, let's try a good one.
items. Total cycles is 4 plus 999, which is 1003. And the clock period is 160 plus 5, 165 nanoseconds. So total time is 1003 times 165 nanosecond.
Could be 1. False. This is not clocks. This is actually a good one. You guys will for sure like it, and let's try it. If you can't, we'll take help of ChatGPT or Claude, and let's see. Okay, so question says comparing the time T1 taken for a single instruction on a pipeline. So with okay, so this question seems like obvious, no? is actually not that obvious. Let me think. I picked up that question just because I saw a lot of upvotes in that question. For that question, that's why I picked that up. And I can generally think it might seem like in the first row that if you see the question comparing the time t1 taken for a single instruction on a pipeline CPU. Now here t1 is pipelined for a pipeline CPU. T1 is time taken, and T2 for pipeline or a non-pipelined but identical CPU, but non-pipelined. Now, like on the first glance, I also thought that T1 is pipeline, T2 is non-pipeline, so it has to be C, right? T1 greater than T2, because come on, pipeline will always take less time. But the trick here in this question is, it says single instruction. Now, for a single instruction pipeline, let's say we have 5 stages, 3 stages. Let's take a fewer stage. This is, let's say, non-pipeline, and this is, let's say, pipeline. Let's say this takes 3, let's say this takes 2, let's say this is 5, so 5 is the, like in that case we don't care about which one is slowest, we just take the sum of all the classes and add them, so that will become 10, and will multiply with clock cycles. So 3 cycles, 3 plus 2 plus 5, 10. 10 into, let's say, clock cycle is let's say 2. So 10 into 2 will become 20, right? But yeah, it's actually saying for single instruction. So for single instruction, let's say this is 3 to 5. So yeah, for single instruction also it will take 3 stages, not so. Will take 1 into 3, but the catch here is it can have overlaps. So let's just like get a concrete answer from ChatGPT to make you guys understand that why for a single instruction pipeline it would take more time. Okay, so let's just see.
Секунду, сейчас посмотрю. Да, именно. 3 больших...
What distraction?
A quick look and then summarize? Yeah, exactly. The 3 large rectangles are the actual work. Pipeline stages like S1, S2, S3, the small blocks between them are pipeline registers. They don't do computation, they just store results each clock tick so the next stage can work.
Okay, now I'm sending you a question. Just go through it and explain.
Sure, send it over. I'll take a look and then summarize it. Sure, here we go. The image shows a multiple choice question about the time for a single instruction on a pipelined CPU versus a non-pipeline one. The correct relation is T1 is greater than or equal to T2, so option B. That's because pipelining doesn't reduce the latency of the single instruction. It mainly improves throughput. So for one instruction, the pipeline CPU takes at least as long, sometimes slightly more due to pipeline register overhead.
You guys might have got it, but let me show you with an example. Okay, let me take this example for you guys. This example. So it says take a simple example with 4 stages S1, 2, H2, 2, S3, 2, S4. Non-pipeline CPU or instruction has to go through all, so 2 into 4. Okay, so only one instruction, right? Yeah, so only one instruction given in the process, and one instruction. So 2 plus 2 plus 2 plus 2. So that will become 8. Yeah, so this is for non-pipeline. One instruction. The pipeline CPU now split this pipeline. Split the 4 stages into pipeline stages. That's but a single instruction still has to pass through that 4 cycle. Clock cycle is 2 nanoseconds. Yep. Clock cycle would be 2 nanoseconds plus the slowest one have to take, and 2 is the slowest one, yes, so it will be 4 into 2 as 4 cycles, therefore 2 equals to 2. Yeah. But we can have overhead also. If we have overhead of, let's say, 1 nanosecond, in that case we have to take 4 into 2 plus 1. 4 into 3 becomes 12. The overhead is there. So yep, T1 is not always equal to T2. Yep. So this was T1, pipeline 1. This is T1 and non-pipeline was T2. So you can have T1 greater than equal to. So basically this is wrong. B is the correct answer, right? Okay, so let's wrap it up today. We can go for like more tomorrow. Okay, we'll cover a lot more tomorrow. More tomorrow. Okay, we'll cover a lot more tomorrow. Okay then, bye bye guys. See you guys tomorrow. Good night.